robot systems, we very often talk about task allocation. It's kind of a very general term used for task allocation, resource allocations, lots of different things. And there are a lot of algorithms, lots of papers, a long time. So what I'm trying to do is kind of look at algorithms that can scale very well. So many methods work for 10 robots and tasks would like to get in hundreds, much larger numbers. So scalability is kind of important issue. The other things I'm interested in is algorithms that are less failures of robots. We all know, to do real robotics, we all know the robots never work. They fail wrong times, they disconnect, or whatever. And so we want to make sure that the algorithms are as fast as possible. Now, one of the assumptions that I'm making, and I think everybody in the robotics is making, the robots are kind of friendly to each other, willing to collaborate, so we're not going to look into any of the theoretical issues. If you know, if I'm working with another robot, I can trust the robot, enemies might leak, do bad things with me. This is all out. I mean, it's like no different. So again, we're soon collaborative. So, two specific things I'm going to talk about are just some recent work done with students. One is allocation of tasks. Not only acquisition space, but there are robots which task is location space, but also have temporal constraints. And we like to stress temporal constraints in the kind of general form we were using scaling, in which we describe them as time windows in which tasks must be executed. And in fact, we not close any restrictions on the time windows. We have small time windows, big time windows, high time windows, overlapping time windows, any kind of time windows. And the other challenge that we look at is tasks that have a cost that is not fixed, but in fact grows with time. If you think about it, that task, and the cost of doing the task decreases with time, I can just be lazy, I don't do anything, right? At some point, the cost goes zero, I'm done. But if the cost increases with time, I have to be much more careful when I do my allocation, because if I'm lazy, if I'm doing it right, then my cost is going to go. So again, those are the two kind of topics. So we start with the allocation of tasks with the temporal effects. This is kind of a very simple my student likes this stuff. Things show up one at a time. So this is just very simple example. Just to be they have a number of robots. Use in general the grid environment is very small. We have a number of tasks in different locations, and each of the tasks has an expected duration and a time window. This kind of time windows are used in the multiple vehicle routing problems with time windows, right? In which you have, starch tracks to go around and deliver to customers or so, and each of the deliveries to the side of the windows. So you tell the customer I can't do 8 or 9, and so that's what we have. Those things in general are not in the robotics, and that's kind of the component. Now, what I like to do, typically we're looking at minimizing the finish time of the last task, which is called the make span. But we also minimize the combination of minimize the make span and minimize the run distance. Or we can do some other things. Those are the two major objectives. Most of the work that exists out there minimizes the distance time. I in general want to optimize or find out a solution to minimize the distance of the time. When the time comes into the picture, things get a little more complex. And in fact, the reason why things get more complex is because the constraints between time and space make conflicts. You can have tasks which is very close by, but has to be done very late at the time. Tasks that are far away have to be done quickly. So again, those two constraints are kind of different tasks. There are some centralized solutions, particularly there's a mixed engineering programming, but they don't scale well, and again, the more fields that they computers, so we kind of like to come up with distributed solutions. There's another issue, and centralized solutions in general work well if you know all your tasks are on and you're scheduled in advance. When things change in real time, the new tasks around, so centralized solutions are a little bit more complex, and there are methods of developing actions. So But again, I was kind of interested in distributed solution and basically heuristic solutions. So we're not going to guarantee optimality result, but we try and enter something. So we have so we come up with we're going to present this next week at AAA. But this is just a very quick outline. Is now called SC, temporal sequential single item option. So it's an algorithm based on use of options, which is a method that's been used by many people, including many people in this room, for task allocations in the robotics community. We start from the sequential single item option algorithm, Robotics, other people, and kind of extend it to include the temporal positions. And what we do with each robot uses what's called a simple temporal network, which is kind of a data structure that has been developed in the backend with a number of years to keep the schedule consistent. So basically, the algorithm is the same with sequential single item options, uses simple temporal networks which robots maintain consistency. And then we can get two different heuristics for using mid span or mid span and heuristics. And again, one of the important features is that this algorithm works. If I have all the tasks up front, so I can really try to do allocation or task alignment. So again, just to give you a quick idea here, this is again this simple example I had before. Even simpler, I have two robots here, I have two tasks, and we're showing down here what we call the time windows for the tasks. So typically they can start with schedule community. You have an early start time, you have a late finish time for the tasks, and you have the expected duration. So task one can be done any time between this and this time point, and this other part will be its expected duration. That's a bit long and relatively flexible, starting with a middle ground. Same for task 2, task 3, and task 4. So depending on the time windows and the spatial distances, when we run our algorithm, we may end up with an optimal solution and a suboptimal solution. Don't guarantee the time. So this obviously is an example built to show that yes, we can introduce optimal solution. And what to show here at the bottom in this case is this robot is going to go here and then here, this robot here and here, and what shown down here is the scale. So since this robot has the power to do the first task, even though the first task is start at the beginning, the robot is not going to be there. So the earliest the robot can get there is this point. So it shows here the timeline is the robot is traveling, which is the task, does the task, is traveling to the next task, does the task, so, and then there's an extra scale part. And the same for the robot. So the complicated part here is that you have to take into account the travel time. And make sure again, if you allocate all the tasks in such a way that you get this travel time. So again, I hope this gives you general idea. I'm skipping the details of algorithm. I think there's one kind of important, interesting part in which basically when each robot, I mean, we have option here, the robots repeat very standard methods. When a robot decides to do the task, basically there are two kind of important ideas. One, I'm a robot, right? I already got one task, and I have my schedule. Like, you know, all of us have schedules, and we fill them up. And the first thing I'm trying to do, I'm trying to see what's the best place in my schedule where I can put this new task. Can I put it? Or do I have a conflict? If I have a conflict, you know, if I can put in, I try to find the best place where I can put it. And that's the, since I'm trying to minimize the end time, is early. As early as possible, that means, you know, try to keep my duration of my schedule as fast as possible. And so that's this part here, find the best insertion point for the task. Well, there's one other thing that we do, and sometimes, again, think about this is something we do all the time, right? I have a meeting, I have another meeting, I have 20 minutes in between, I need half an hour because I have to do something else. Well, what do? I just push something around, right? You can say, okay, can I push this a little bit earlier, push this a little bit later? Since each robot keeps its own schedule, and we use these simple temporal networks, which, for those of you who haven't seen these graphs, in which you specify temporal constraints between the start and the end of each task. So here, suppose I have already this task allocated, I have this task allocated, and I have some time in between here. Now I'm trying to see, can I fit in this new task? And to fit in a new task, I have to make sure I have time to travel to this new task, do the task, and travel to the next task. And again, we can use the simple temporal networks to make sure that we don't have constraints, which is the reason why the simple temporal networks helps us. Because basically guarantees that the constraints are not violated. This allows us, again, to push things a little bit as long as we're still within the constraints. So I can push the first task before it's initial or the start time. Again, this is what the SPN will guarantee. So just very, very quick, just kind of moving to the next things. So we compare the results of the two algorithms, and one is the consensus-based bundle option algorithm, MIP, which assigns multiple tasks and doesn't have an option here, but the robots come up with consensus by locally reorganizing the task. And one is kind of greedy assigning. Again, I'll go through very quickly a few of the results and then move to the next topic. So here we show two different data sets. Those are synthetic data sets. Variable number of tasks, fixed number of robots, this number of tasks, variable number of robots. And we're going to show this is our algorithm. So here you want to be high because you want to allocate as many tasks as possible. One of the things that often people do in this kind of domains is you may have more tasks. So we're not guaranteed that all the tasks are good. So one of the metrics we use is count how many tasks. And again, this shows really increasing number of tasks. If there are few, I can do all of them. Once I get to 100 tasks with 10 robots, typically I can't do all of them. We're trying to find an algorithm that's the largest number. So red feels interesting. And this is similar. So again, in the case of we just kind of vary. We also tried, I mentioned that this algorithm works also when tasks arrive as the robots are executing things, and we expect them to arrive in batches, which could be one task, or could be more than tasks. And this again shows when the tasks arrive in batches. And what you expect is if you have multiple tasks coming at the same time, you can do a better allocation. If you have one task at the time arriving, and it is being done very quickly, there's not too much time for robots to adjust their states. But this again shows that we're doing better than the other one. And finally, we tried algorithm with the data set, which is using the data routing community. And Windows is called the Solomon data set. It's very large data sets with lots of examples that cover a bunch of different cases. So the example shown here is when the tasks are clustered location-wide. So in fact, all the dots here indicate where the tasks are. And the time windows are tight, so there's not much slack in the time windows. And this shows, this is a specific instance of this data set. It shows the allocation that our algorithm does, in which, as you see, each column indicates a robot. So you see the list of robots here. So we see that the algorithm really allocates clusters to the same robot. And well, this is what the CBDA produces, and this is what the greedy algorithm produces. And because the greedy algorithm starts allocating one task per robot, once they all end up here, then they're all kind of stuck there, and there's no time to go do it. So again, this is just to be visually, and this is a kind of allocation like to do, and just comes out sort of naturally from the outcome. Okay? We also tested, and we have the second algorithm, Dual, that has dual objectives to maximize the number of tasks and minimize distance, and it's also that. So just to summarize. Next topic. So again, we look at the distributed task allocation and show that the algorithm is better than other algorithms, and obviously there's a lot of stuff in there. Now let me kind of move to the second topic, which is even newer. We started working on this about a year ago. So the pictures here, which we started, come from the RoboCup Search and Rescue competition. I don't know how many of you. It's always called the Asian RoboCup Search and Rescue. And basically you have city, you have buildings, streets, and so you have a number of agents, different types. So the red ones are fire trucks, the blue ones are police cars that can clear blockages, and the white ones are ambulances. you have green dots, there are people who are alive, and when they become black, they're dead. And if you become lost, then you still get some credit for collecting dead bodies, but we rather have live bodies instead of dead bodies. And one of the problems, specific problem looking here, is fire. So in general, in robotics, at some point the fire starts somewhere, and you have to go and extinguish. Fires have these properties that you tend to grow over time, so if you don't get there very quickly, you can burn an entire city. And the black part here shows the entire city. And here, again, without armoring, you can contain the fire, because you can't go there. So I'll give you a high-level idea of how the method works. So what we do here, we model the cost of the task as a recurrence relation of time. So the cost of F for the task I, time t plus 1, which depends on the cost of the task at the previous time interval and the number of robots that you have that are working on the task at time. So we model this as a recurrence relation, which you can model if I know the cost of the task at time t, and then I compute the delta, how much is going to grow, then I have the cost of the task at time t plus 1. And to model the growth, well, there is a growth function that we assign from, say how fast it will be exponential or whatever, minus the amount of work that the agents are going to do. So if I have n sub IT agents, and each of them does the same amount of work, which goes out of view, and each step, of course, grows, except if I do some work, I reduce. Now here we make a bunch of assumptions. Basically, in this case, we assume all the growth functions are the same, just to relax the assumption. We assume the growth function is positive, definitely convex. Now, if you assume that the travel time is the same, which is a big assumption, and we also assume we have more robots in tasks, now we can show how we can reach a time when the cost of the task goes to 0. Just to give you the intuition, this is an example of a function which has this growth, right? So if I don't do anything, I sit there and watch. That's over time, that's how much it's going to grow. Now and this is, again, I don't do any work on this fire or whatever it is. If I start putting some number of agents, and each of them has capacity to work, then I can reduce the growth. So it becomes like this. In this case, with 10 agents, the more agents I put, the more I reduce the growth. And at some point, I want to find a time at which my growth reaches 0, which means I reduce. So the tricky part is how many agents do I need to allocate? So the more agents I put, the faster I do. Now, in general, if I have only one fire, lots of agents, they all go there, we're done. But in general, I have multiple fires, not enough agents, so I have to kind of decide which one goes where. So we come up with the kind of algorithm that and prove that to minimize the total growth is sufficient, again, with the assumptions we made, to assign agents to tasks that minimize the cost growth. Again, I find a task that has just been more English, so I find a task that I expect to finish last, and I assign an agent to the task. Assigning an agent to the task is going to reduce, right? And I keep on doing this until I assign all my agents. And when all agents are assigned, the algorithm terminates, and this is the optimal solution under the assumptions. Now, in reality, I'll finish. In reality, things are a little more complex, because in reality, I don't want just to do the allocation up front. I have to do it. This is an example again from Robotics, in which you create clusters where we send a bunch of robots. Again, just trying to show you a quick results of what is called RT-LFF. So last finishing first is our theoretical optimal algorithm. We do a real-time version, so we keep on repeating applying the same algorithm, because my predictions of cost growth may be correct, or some robots failed, firecracker can disappear, go on fire, or whatever. And so we keep on reapplying things. And final one, this again, you can compare this real-time late finishing first with 3 different kind of heuristics. You know, you assign like all the agents to one fire or to a uniform distribution, or just assign to the lowest one. And in general, again, these are 2 maps, and the blue, which is this algorithm, tends to be much the best. Okay? So, summary, and done. So again, we model the growth tasks. We have this optimal solution with very strong assumptions being the same private cost, which you must improve. And then we have these real-time solutions in which we account for the real-time travel, things like this. And that's the end.
Any questions? So for the task allocation, I'm going to come to the fire. What is their task?
So the fire trucks have to, they fill up with water and they have to go close to the fire enough and shoot the water on the fire. And how much the fire grows or decreases depends on the amount of water that comes in, which depends also on the distance of the trucks. And so if you have only one fire truck, in general, again, because of this exponential growth, you reduce a little bit the growth, but not enough, and so the fire expands. And then depends on the buildings, if they are wood or if they are concrete. I mean, there are a lot of other factors in the issue. But that's really the issue. So you need to send enough fire trucks in place, but if you have multiple fires, where do you send them? A small fire, a big one, how to allocate, and that's this argument.
So it's modeled like the spray system?
Yeah, yes. In fact, we do the modeling, and this is kind of highlighted, we do the modeling of